So last time we were talking about resistance, fin resistance. I just a couple things to finish up here. I think it's not super important that we go through all this in detail because you actually did this yesterday in discussion. So I'm going to really race through it so we can get to the other stuff. But I just want to make sure that I talk about it. So we were talking about fin resistance. Maybe one thing that I want to say here is that, again, I said it last time, but I want to reiterate. Fin resistance is not the resistance from like the center line of the fin out, right? That's not what it is. Fin resistance is an effective resistance from the base, right? The base of the fin, the footprint of that fin. It's the effective resistance from that part out to the surroundings, accounting for the fact that you have all this extra, basically free area associated with this fin. Right, so think of it like you're replacing, let's say it's the circle of the footprint of the fin. You're replacing that with a bunch of extra area, and there's an additional resistance associated with getting the heat out, right, to that extra area. So when you're calculating the BO number, when you're calculating these like preliminary values, that's just to justify the extended surface. The fin resistance is something else, right? It's this whole idea that you are adding area, but there's a resistance to get out to that area. Okay, so you have the fin resistance. We have this model. We've so far talked about this adiabatic tip assumption. Now if we have a fin where there's not an adiabatic tip like you have in the homework, let's say there's convection from the tip, you should know how to deal with that. So you've gone through this already a little bit in discussion, but let's just, again, cover it. So if you have convection from the fin tip, let's think about the boundary conditions that are involved in this model. The first boundary condition, which we're now familiar with, is, say, a specified temperature. So T at x equals 0 is equal to TB, the base temperature. That is a statement of the boundary condition that's not actually enforcing the boundary condition. Right? To enforce it, we have to actually write out the equation. BC2 is now, instead of it being adiabatic, it's this matched rate equation, which looks like this. So we would say, so let me sketch something out. So you have the end of the fin here, and we're talking about like this infinitely thin energy balance on the surface of the fin. So you have coming into this end, sorry, it's kind of echoing here. So coming into the end of the fin, you have heat flow due to conduction. Leaving the end of the fin, you have heat flow due to this whatever rate equation, or convection or radiation. This control volume is infinitely thin, right? So there's no heat loss from the top or the bottom of this control surface. Sorry, maybe I said control volume. This box, this green box, is my control surface. So I'm just looking at what's coming in and what's leaving. It's infinitely thin. Unlike our differential control volume, which has a thickness, dx, the surface is infinitely thin. So you're trying to match what's going in to what's going out exactly, right? So there's nothing leaving the top or bottom. So when we state this boundary condition, we're just saying, okay, conduction has to equal the heat loss to the surroundings, in this case, convection. And then I just need rate equations for those two things, right? So control surface analysis, again, is different from control volume analysis. We always do for the boundary conditions control surface. Okay, so write this out. It is conduction minus K, AC, dt, dx at x equals L, for example, is equal to, that's our Q dot conduction. Q dot surroundings is just convection. So H bar, A of the tip, let's call that, A tip, times T at x equals L minus T infinity. So you see, we've matched the rate of conduction to the rate of convection. In your homework, you have convection and radiation. And then we've got the areas associated with each of those. So AC in this case happens to be the same thing as the A tip that we've written. So those would cancel out. Right? So you can cancel these out. We could keep going and like kind of write this out. What you do is you take your temperature solution, you substitute in, take the derivative, substitute that in, and then evaluate it at x equals L. Yeah. So I'm not sure I fully understood your question.
So like, the way we calculate the resistance of the fin was just looking at convection. Would it change if we also looked at radiation as well?
Yeah. So the resistance of the fin up here would need to include all possible heat loss mechanisms from the surface that's exposed. Right. So your fin resistance is saying, I've got some area, I have heat loss from that area. That heat loss could be convection and radiation. And then I've got an eta fin that like kind of like scales that, right? So yeah, in the case where it's not just convection, you have to add the other stuff in there, and then you'd maybe use an equivalent resistance or like a total resistance model or something like that. Yeah. Okay, so we'll just jump to the end here. I mean, you can substitute the temperature equation in. What you end up with is this like fin efficiency that looks a little different. So this is, I think I've given you this before, so I'll just write it out, but it's tan h, hyperbolic tangent. So tanh of ml plus ml AR tip. That's the area ratio of the tip. I'll give you that in a second. And that's all divided by ml times the quantity 1 plus ml AR tip. Tanh of ml and of quantity, and then times 1 plus AR tip. So then this AR tip thing, AR tip, that is AC over perimeter times L. So this is like the previous version of this eta fin was assuming adiabatic tip. That was just tanh ml over ml. So if you look at what happens, so if AR tip is very, very small, that's saying that the ratio of the area of the tip to the area of the rest of the fin is really, really small. That goes to 0. What happens to this equation? Well, that ml times 0 in the numerator, then you have ml times 1 plus ml times 0, so that second term goes away, times 1 plus AR tip, so that's just 1. So it converges to the same thing. Right, so this is just like a modified version for heat loss from the end of the fin. This is what you'd probably want to use for your homework. I think I gave you this in the prompt. Okay, so that kind of covers fins, fin resistance, just like basic stuff. You want to kind of be comfortable with this. The other thing I want to talk about real quick is this fin array idea. You did this in your discussion, so again, I'm not going to spend a huge amount of time. One thing I want to say is when you're developing a fin array model, what you're trying to do is create this resistance network. And the resistance network includes usually like conduction across the base, and then the loss or the heat rejection into each of the fins individually. So you have, let's see. So if we were to draw a resistance network for this, let's say we have, I'm going to add something over here because I think it's important. So we have TB. TB is the temperature right at the base. Let's say we have some other T. Let's call this, I don't know, let's call this T battery for no good reason. T battery over there. So let's say we wanted to understand or develop a model that relates T battery to the surroundings. Well, you can do that. You just have to account for all the resistances that are between T battery and the surroundings. So if I drew a network, say T battery here, I'm going to have some resistance between T battery and TB. Those are different things. In a homework problem, that might be multiple resistances. In this case, we just have, let's say, a conduction resistance here. So then this here is TB, right? That's the temperature at the base of the fin. Now once you get to the temperature of the base of the fin, there's multiple paths for heat to go out. You could go out one individual fin, another individual fin, or you could go directly from the base to the environment. So we'd have, like, say, first pathway, this would be R fin 1, second pathway, R fin 2, and so on, down to R fin N. All of these are going to a single temperature T infinity. And then you also have this extra base, like the base area also rejects heat. So we'd say here, a parallel pathway would be R unfinned, right? The resistance of that unfinned area of the base. So you have to account for all of those. Normally, when you say like a resistance network for an array, we're just talking about this stuff here. But I've added the extra one in just to show you what it looks like. All right, so you have stuff in series and you have stuff in parallel. We write it out, for this example, it would look something like this. So R total, I'm going to just write for the green part, right, just for the array. So R total for just the array is something like this. It's all these things in parallel. So we have 1 over R unfinned plus 1 over R fin 1 plus 1 over R fin 2, plus 1 over R fin N. All that to the minus 1. Okay, so you're going to have to compute the fin resistance, like RF1, assume that they're all the same probably, right? RF1, RF2, and so on. All those would be the same. You compute the fin resistance using the fin efficiency model. You then take n of those, right, because there's n of these 1 over r's. Add that to the unfinned area, take the inverse, and that gives you the total array resistance.